Hello. The topic for this week is one-way between groups analysis of variance. And because of a family situation that I have to take care of, I have to either cancel the class or move the class to online asynchronous. And I have talked to the department chair, Dr. Furtak, and also the dean, get the approval from the dean of the college. And it seems to be that it will be least disruptive to students, and that if I move the class to online asynchronous. And this change will affect this week's class only, and it does not change any of the homework due dates. And so after this week, of course, there's the spring break. So I'll see you after the spring break. We'll resume in-person instruction. Okay, so for this week's class, I have prepared 4 videos. So this is the first of the 4, and we're going to introduce the ideas, the concept, and the logic of the analysis of variance. A little bit of historical background, and then we're going to focus on the logic of analysis of variance. And then from video number 2, 3, and 4, we're going to have 3 activities. So each video is going to be devoted to one of the 3 activities. And you have the normal, the regular homework, the quiz, and also, of course, Scikit-learn is also due by the end of this week. And you have the usual activities. So instead of handing out the worksheets in class, I'm going to post these worksheets on the Canvas page, and you can download and work on those problems as you watch the videos. Okay, so that is a brief introduction, and let's talk about analysis of variance, or ANOVA. And it's one of the common acronyms that people who have a background in statistics would recognize that instantly. Oh, ANOVA. So we're talking about ANOVA, that analysis of variance. And I believe this is a screenshot from Scikit-learn. So basically, what this is about is how do we decide which analysis to conduct. Kind of the first question, of course, you ask is how many sample means do we have? If you have only one, and then the next question is, do we know the population standard deviation? If yes, it's 1 sample, z-test. If it's no, 1 sample, t-test. Now, what happens if we have 2 sample means? I'm going to grab a pen. Okay, so what if you have 2 sample means? Well, then the next question is, are the samples related? And if they're not related, then it's independent samples t-test. And if it's related, paired samples t-test. Or if you have only 1 sample, right? You still have it's paired samples t-test. So that's what we discussed last week. Now, for this week and also the next week, the week after spring break, we're going to devote the 2 weeks of time to discuss analysis of variance. So the basic situation is that we want to compare 3 or more sample means. And then the next is the same question. So how many independent samples do we have? If we only have 1, then next question is, are the samples related? And if you're not, then it's one way between groups ANOVA. That's what the topic for this week. And if the samples are related, then that's one way within groups ANOVA. That's the topic of the week after the spring break. And we're going to just, in class, we're not going to actually discuss the factorial analysis of variance, because that's the topic reserved for some more advanced topics, reserved for maybe Psych 121, or those of you who are really interested in statistics. After 121, you may take 102. That's when we formally discuss factorial analysis of variance, which deals with kind of situation that we have 2 or even more independent variables. That's just more complicated, more complex situations. However, we are going to use one way between subjects, factorial ANOVA, that's topic number 12. We can use that as an extra credit opportunity. So at some point after we finish discussing ANOVA in class, I'm going to release, unlock that the extra credit, which basically means that if you finish the Scikit-learn module T12, that's on the topic of factorial ANOVA, then you get extra credit. So, but we're not going to spend time in class. That's true. We just don't have time for that. Okay, so let's talk about why is ANOVA necessary. So why t-test is not enough. T-test is a great test, right? So anytime we want to compare two sample means, we can choose depending on the design of the study. We can use either pair samples t-test or independent samples t-test. So why do we need ANOVA? The basic answer to the question is that we can have sometimes more complex, more complicated situations. So for example, if you conduct an experiment and the independent variable has two or more conditions, so you end up with two or more sample means. And in that case, t-test cannot be used to assess overall differences. And also another problem is that repeated t-tests will lead to increased family-wise type 1 error. So that's something that we're going to discuss a bit later. So here's the situation. Let's say you set up 3 different conditions. Okay, and condition number 1, you provide the participants with positive feedback. And condition number 2, negative feedback. Control condition, no feedback. So 3 groups, and you have 3 sample means. And the null hypothesis in this case would be mu1 equals mu2 equals mu3, which is not surprising because the null hypothesis always says there's no difference whatsoever, right? So in this case, we have 3 sample means. The corresponding null hypothesis would be there's no difference between any of the population means. So mu1 equals mu2 equals mu3. Now, the question is, how do we test this? T-test would not be good enough because only t-test can accommodate only 2 sample means. So if we are forced to use t-test, then the only way that we can perform this task is first, we ask, does mu1 equals mu2? So that's 1 t-test. And next, does mu1 equals mu3? That's the second t-test. And then does mu2 equals mu3? That's the third t-test. So we can conduct 3 t-tests in this case. Now, what if we have 4 conditions, 4 sample means? Then, believe it or not, the number of tests that we are going to require, we're going to need, is going to increase rather quickly. With 4 sample means, we have to conduct 6 t-tests. Now, the problem with these repeated t-tests is that increased type 1 error, overall type 1 error. So the idea actually is very straightforward. If each t-test is conducted at alpha equals 0.05, meaning you can make maximum 5% type 1 errors. Now, what happens if you conduct 6 t-tests? What is the upper limit of the type 1 error? The answer is it's going to be way higher than 0.05. Okay, it can go as high as 0.05 times 6, 0.30, which is obviously not acceptable. So that's the idea about repeated t-tests will lead to increased family-wise type 1 error. The other issue is that what if we are not interested in the pairwise comparison? We just want to know overall whether there is a significant difference or not. Multiple t-tests cannot be used to answer that question. So one scenario in which t-test is not enough is when we have more than just 2 sample means that we want to compare. So that's kind of one scenario, and there's also in other situations, more complicated design, that t-test is just not adequate. So what if experiment with 2 or more independent variables, which is quite common in psychological research. So here's an example. This is a study published in 1996 in a journal called Applied Social Psychology. And they asked a very straightforward question. So the question was, what if let's say, suppose you are a waiter or waitress, you are a server at a restaurant, and you decide to draw a smiley face when you give when you bring the check to the customer. So you draw a smiley face, right? So that's the smiley face condition, and you also have a control condition in which you don't draw the smiley face. So that's one independent variable. They just want to know what is the effect of drawing the smiley face on the check. What does that affect the amount of tip that you receive? Okay, the dependent variable in this experiment is the amount of tip that the servers receive. And they did include a second independent variable, which was the gender of the server. So the server can be male and the server can also be female. So as you probably recall from research methods class, now we're looking at a 2 by 2 factorial design. We call this kind of design a factorial design. You have two independent variables. It's a two-way factorial design. Now, we end up with 4 sample means. So male control condition, female control condition, male happy face condition, and a female happy face condition. Okay, so that's the mean, and in the parentheses, those are standard deviations. Okay, so we have the basic data. Now, the question, of course, the question they're most interested in is, what is the effect of drawing a smiley face on the amount of tip that you receive? Now, the answer, if you look at these means, the 4 sample means, is actually quite complicated. Because looks like drawing a smiley face has a different effect depending on whether the server is male or female. So for male servers, they received 21%, 21.4% if they don't draw smiley face. When they draw happy face, smiley face on the check, they received 17.78% tip. So it looks like either there's no effect, or if there is an effect, it's not in the direction that you would like to see if you were a server, right? However, the results looks very different if you look at the data for the female servers. So when they did not draw smiley face, on average, they received 27.78%. And when they did draw a smiley face, they received 33.04%. So it looks like the drawing a smiley face had an opposite effect on the amount of tip servers receive depending on the gender of the server. So we call that interaction. Okay, so the definition of interaction is that interaction occurs when the effect of one independent variable, such as drawing a happy face, depended on another independent variable. In this case, it's gender. So in this kind of factorial design, how do we analyze the data? Well, we can't use T-test. Okay, T-test does not allow us to test directly the interaction effect. So we have to use analysis of variance. So that's when kind of another situation where ANOVA is appropriate. Okay, so some history about analysis of variance. Ronald Fisher was one of the probably, if you have to name 2 statisticians that made a great contribution to statistics. If you have to name 2 people, then Ronald Fisher has to be one of them. The other one is Carl Pearson, who was the guy who came up with this correlation coefficient and also regression analysis and etc. So Ronald Fisher is the one who came up with analysis of variance. And interesting enough, his contribution was not limited to ANOVA, which is the method of analysis. He was also the one who came up with this idea of random assignment, and which is a fundamental principle of experimental study. So that's what set apart an experiment a true experiment versus a quasi experiment. Okay, so random assignment. He was the guy who came up with this idea, and of course, he was also the one who came up with, who designed this methods of analysis called analysis of variance. And actually, the test or the test statistic carries his name. We call this the F test. F for Fisher. So it's his test. And before we discuss this method, let's just say very quickly, for between groups ANOVA, it has the same three assumptions for independent samples t-test. Number one, independence. All the data points are independent of each other. Normal distribution. So the dependent variable conforms to a normal distribution in the population. And number three, homogeneity of variance. There's no difference in variances across the different populations. So that's the homogeneity of variance. So the same three assumptions for independent samples t-test that we discussed last week also applies to between groups analysis of variance. Okay, so the basic lesson plan. So this video, we just talked about why it's necessary and a little bit of a history of ANOVA, kind of historical figure. And then we're going to focus on the logic of analysis of variance and partition of variance, the F statistic, the F distribution. Activity number 2, we're going to go over a complete example of F test. Now, when the F test tests the overall difference, we call that omnibus F test. And we are going to also introduce a new measurement of effect size called eta squared. When we conduct ANOVA, we don't use Cohen's d, we use eta squared. And then the activity number 3, 10-3, post-hoc comparisons. We are going to introduce some of the ideas, family-wise typo and error, two-case HSD, how to interpret SPSS output, and report the results in APA style. Okay, so we're going to have 4 videos. The first video is the logic of ANOVA, and then 3 sort of activity videos, one devoted to each of the 3 activities. Okay, so now let's talk about the logic of analysis of variance. We're going to start with this simple situation in which we have a experiment with 3 conditions, and treatment 1, treatment 2, and treatment number 3. And we randomly assign participants into those three different conditions with sample 1, sample 2, and sample 3. Now, in this case, in this example, the sample size equals 15, 15, 15. So they're all the same. And the sample mean looks a bit different, 23.1, 28.5, 20.8. And sum of squares, sum of squares, sum of squares. And of course, we understand sum of squares is something that will lead to variance, right? If you take sum of squares divided by degree of freedom, we have variance. So this is the basic information we have, of course, as the researcher somebody who conducted this research, they are interested in knowing not about these sample means really, but it's inferential statistics. Our question is really about the population means. So what about mu1, mu2, and mu3? The null hypothesis in this case is mu1 equals mu2 equals mu3. And with question mark, meaning that's what we need to find out based on the sample data, right? And of course, what we're trying to test is the null hypothesis mu1 equals mu2 equals mu3. And you may ask, well, what about the variance? What about population variance? Sigma 1 squared, sigma 2 squared, sigma 3 squared. Well, that's equal. That's the homogeneity of a variance assumption. That's the statistical assumption. We assume there's no difference in the variances. The only difference, if there's any, is in the population mean. Okay, so this is the kind of the basic situation. Now, let's think about these sample data. So 3 samples, right? So this is just a kind of a visualization saying, oh, okay, so here is a distribution for the first sample, for the first group. So mean M1. This is the mean for sample number 1, condition 1. So basically, you're looking at the distribution. It's a normal distribution, and the mean is in the middle part. We call it M of 1, right? That's your sample mean. Now, within that sample, obviously, not everybody perform at the same level. That's why we have this distribution. The same thing also applies to the second condition. You are looking at this distribution, and not everybody in the same who received the same treatment have the same score, the same. So again, you look at the distribution. Same thing applies to group number 3, right? So this is just a 3 little distributions for the sample data. Now, our real question, of course, is that are these 3 sample distributions came from a large distribution, came from the same distribution? We call that the null distribution, right? Under the null hypothesis, mu1 equals mu2 equals mu3, right? So in that case, there's no difference. There's only one distribution. So that is represented by this big distribution in the background. It's the red. So this one represents under the null hypothesis. Under the null hypothesis, mu1 equals mu2 equals mu3. So these 3 samples are actually drawn from the same population. Okay? So for that population, for that distribution, we have something called M of T. So the mean of the total. So meaning we combine all 3 groups, all 3 samples, combine them, then we have this big group, and the average of everybody, right? So if we have 15 here, 15 here, 15 in this group. So total 45. So the average of all 45 participants, and we call this mean M of T, T for total. So we can also call this the grand mean. Okay, this is also referred to as the grand mean. I do apologize. This is awkward. I'm trying to use a mouse to write. So this is the grand mean. We call it M of T. And of course, that's the null hypothesis. The alternative hypothesis, you call it H of A or H of 1. Either way is fine. The alternative hypothesis is that not all mu's are equal. Now, we're not saying that mu1 does not equal mu2 does not equal mu3. We are saying not all mu's are equal. Another way to describe the alternative hypothesis in an ANOVA is that somewhere there is something that's different. Maybe everything is different. Maybe there's a difference is between only 2 population means, but doesn't really matter. The point is not all population means are equal. So that is the alternative hypothesis. And of course, we have to decide based on the sample data whether to reject the null hypothesis or to retain the null hypothesis. So this is kind of one scenario. And of course, we can think about kind of this scenario. So for example, what if M1, the group 1 is here, group 2 is here, and group 3 is like way over there, right? So this is a scenario in which probably it would be more evidence to maybe reject null hypothesis. And this will be another scenario in which the sample means are further apart, right? So the mean for group number 3 is further apart from the grand mean, and this one is also far away from the grand mean. So if the 3 samples are drawn from the same population, in other words, if the null hypothesis is true, it will be much less likely to end up with a situation that like this, right? So it's less likely to happen if the null hypothesis is true. And of course, we need to find a way to quantify. We can't just look at these distributions and make a decision. We have to quantify the differences. So how do we do that? Well, it has something to do with variance. So the name, because this analysis is called analysis of variance, is because our analysis actually focuses on variance. So there are two kinds of variances that we can consider in this scenario. One scenario, one kind of variance is we may think about variance between groups, meaning how the different groups, to what extent the different groups are different from each other. So think about group 1. So where is the center of group 1? Okay, it's right here. So what is the difference between M, the mean of the first group, from the grand mean? Okay, this is this much. What about the difference, the distance, or the deviation of this mean from the grand mean? Okay, it's this much. And what about the mean, the group mean for number 3? Sample number 3, okay, it's this much, and it's obviously in opposite direction, right? So this is lower than the grand mean. This is also lower than grand mean, and this is higher than the grand mean. So by using the same principle, we can think in terms of if we subtract M1 minus MT, that is the deviation. And we can square that deviation. And we can do that to each and every one of the participants in condition 1. And we do the same thing for M2, for M3, and we would obtain a measurement, which is basically a variance. But this is the variance between groups. Our focus is to what extent these different groups differ from each other, or to what extent they differ from the common center, from the grand mean. Okay, so that's variance between groups. Now, we can also consider variance within groups, because take the example M1. Within condition number 1, not everybody receives the same treatment, but not everybody perform at the same level. So that's why we have a little bit of a distribution for M1, and we have another distribution for M2 and distribution for M3. So within each group, obviously, we can consider how much variance, how much variation is there within each group. So students or participants, they receive the same treatment, but to what extent their performance is still different from each other. So we can estimate that within group variance. So this is another way to think about it. Okay, so within this group of M2 is sample number 2. There's a distribution, and we can estimate the variability. Now, M2 is also different from the grand mean, right? So that is a distance, that is a difference. And that provides us with a basis to estimate variance between groups. Okay, so here we just introduced two very important concepts in analysis of variance. One is variance between groups and variance within groups. Okay, so between group, within group, and of course, there's also total variance, meaning if we just ignore the group membership and we put everybody in the same big group, how much variance is there in the data? That's the total variance. So let's take a look at let's think about this, what do we have just discussed so far? So again, 3 conditions. Right, so this is actually a sample data for activity 10-1. We are going to use this sample data to hypothetical data set to conduct an analysis of variance. But here, we're just going to present the situation. So the experiment was basically what is the effect of engaging in a phone conversation when you drive. So there were 3 conditions: no phone, sample number 1. Hang out, so you engage in a phone conversation when you drive. and there's handheld and hands-free. So these both are you engage in phone conversation, but use different kind of phone sets. So hypothetically, we had 5 participants in each condition. So their performance 4, 3, 6, 3, 4, and participants in condition 2 that's 0, 1, 3, 1, 0, and participants in condition number 3 1, 2, 2, 0, 0. So obviously, the higher the score, doesn't really matter what the score represents, but the point is the higher score, the better the performance. So on average, participants in condition 1, when there were no phone, average is 4. In condition 2, average is 1. Condition 3, average is 1. Now, when you put all 15 participants, 5, 5, 5, 15, if you put all 15 participants together, you calculate the grand mean, M of T, the mean of everybody, it equals 2. Now, let's think about between group variability and within group variability. So what exactly is within group variability? Now, same condition. These 5 participants, they did not use cell phone. But their level of performance is still a bit different, 4, 3, 6, 3, 4. So not everybody has the same level of performance. Now, within this group, we have within group variance. Same thing applies to group number 2. You see a bit of a variation there, and you see a bit of a variation there, right? It's the within group, or you can say within treatment variance. So what is the reason for within treatment variance, for within group variance? Essentially, you're saying, okay, they received the exact same treatment, but why do they perform at a different level? The answer is that these are just some random, unsystematic factors. Okay, so I mean, you can think of many different reasons why people, even if they have the same condition, they still perform at a different level. And collectively, we just say these are the random, unsystematic factors, and we refer these to as the error, E-R-R, E-R-R-O-R. These are the error variance. Right? Now, what about between treatment or between group variance? What is the reason? So you basically ask the question, why people in different conditions, they have different level of performance. Obviously, one possible reason is that the treatment, right? So people in this condition, they have no phone. In this condition, handheld. In this condition, hands-free. So that's the treatment. And so one possible reason that so the differences may be caused by systematic treatment effects, right? The treatment. And of course, in addition to the treatment, we also have different people in different conditions. So given that they are different people, it's the same reason that we have these random, unsystematic factors that also applies here. So the reason that people across different conditions, they have different level of performance, or this between treatment, between group variance is error. So now we are looking at a situation, what is the reason for between group variance? Treatment plus error. Why do we have within group variance? Error. Now that's kind of interesting because that actually forms the basis for the F statistic that we use for analysis of variance. So the test statistic F is based on a ratio of between group variance divided by within group variance. So between group variance, that's treatment plus error. But if it's only within group variance, then that's just error because there's no treatment here because everybody in the same condition, remember, they have the same treatment. So if whatever causes the difference, it's not because of the treatment, right? So the within group variance is only caused by error. So that's the F statistic. So in order to calculate F, our first task is to estimate the between group variance and within group variance. So that is the, just very quickly, just kind of expand on this idea of F ratio. So F equals variance between group, variance within group, in terms of source, treatment plus error divided by variance caused by error. Now, consider what happens under the null hypothesis. Of course, under the null hypothesis, we say mu1 equals mu2 equals mu3. In other words, there is no effect. There is no treatment effect. Right? So F equals treatment effect is 0, so that's out. And you have a variance caused by error divided by variance caused by error. In the long run, again, this is where the probability comes in. See, expected values, E represents expected. So the expected value of F under the null hypothesis equals 1. Right? F is a ratio. And under the null hypothesis, there's no treatment. So you're looking at the ratio of variance caused by error divided by variance caused by error. So in the long run, they are the same. Under the null hypothesis, expected F equals 1. Now, what about alternative hypothesis? Under the alternative hypothesis, of course, there is treatment effect. Therefore, this part is going to be greater or larger than variance caused by error alone. Right? So, in the long run, again, expected F value in the long run under the alternative hypothesis, it should be greater than 1. Right? No hypothesis, on average, F should be 1. Under the alternative hypothesis, if there's indeed a treatment effect, in the long run, F should be greater than 1. Therefore, when we conduct analysis of variance, we calculate the F ratio, the F statistic. A large F value would provide evidence for rejecting the null hypothesis. So we want, basically, if you want to reject the null hypothesis, get a large F value. So the variance caused by the treatment plus error should be a lot higher, a lot bigger than the variance caused by the error alone. Okay, so that's the F statistic. And of course, we have the F distribution, like t-test, t-distribution, that's just not just one. Instead, there are a whole bunch of them. Each t-distribution is defined by a standard, a degree of freedom. For the F distribution, it's more complicated. For the F distribution, we have 2 degrees of freedoms. One for the between group variance and one for the within group variance. So whenever we talk about F statistic, in parentheses, we always provide 2 standard deviations. So for example, we might say this: F parentheses 2 comma space 30 equals something. Okay, so 2 standard deviations define an F statistic. And so the direction, the region of rejection for F test is always on the right-hand side. However, despite that, or F test is non-directional. Okay, we're going to discuss that later, but here's the kind of just a first exposure. There's no such thing as one-sided F test. So even though the region of rejection for F distribution is always on the one side, but all F tests, all ANOVAs are non-directional. There's no such thing as one-sided F test. Okay, so that is a kind of a brief introduction to the logic of F, of analysis of variance. And so this is the end of the first video. In the next video, we'll go over activity 10-1. We'll show how to estimate the sum of squares. So the first, before we can estimate variance, we have to obtain sum of squares, SS. And we are going to discuss how to estimate sum of squares between groups, and the sum of squares within groups, and the sum of squares total. Okay, so that's the topic of the next video, and this is the end of the first video. The end.